下次如果心情不好，你就去做第一个。
Okay.
然后上课上一上，然后就看到后面去。
We will present a modified branching procedure. The idea is to form a linearly independent set A, U1, U2 up to UM, and construct an orthogonal set of non-zero vectors instead of construct an orthonormal set directly, but we will construct an orthogonal set. All right. Such that W, the subspace spanned by this linearly independent set, can also be spanned by this orthogonal set. Okay? So that Z becomes to an orthogonal basis for the subspace W. Okay? Then we will normalize each vector in the orthogonal set to form the Qi, and then each Qi together, the Q set becomes to an orthonormal set. Okay, so that if we review the Green-Schmidt procedure presented last week, we can see that in each step, to find members in an orthonormal set, we have to normalize the vector in each step. And in a way that it seems like this computational burden is unnecessary. Okay, so we will do it in two steps, okay? And this comes to modify the Green procedure. Okay, so here is the procedure. D1 is equal to U1 plus D4. Okay, and so W1 we find to be the span of U1 is the span of U1. Okay, and U1 is an orthogonal basis for F1. Okay, so that's easy. So the first step is except the normalization, because we do not do the normalization here. Because U1 may not be a unit vector. So okay, so that this singleton is a orthogonal basis for the one. Now the second step, to find the Z2 in the Z set. So we will do it this way with U2 minus the projection, the orthogonal projection of U2 to F1. Okay, so that and so because of the difference will orthogonal to every vector F1. Okay, and so that in this case, such that Z2 will be orthogonal to Z1. Okay. said, since Z2 is either a orthogonal complement of the alright? So Z2 is orthogonal to Z1. Okay. Also, U2 becomes to Z2 plus projection of okay, so that this is Z2, and as we know, the projection of into W1, this is equal to some alpha in V1. Okay? And actually, we will see that I think I can just write it down. So this is the projection of V1, U2, and so this is equal to U2, V1, V1, V1. And here, the identity, we haven't shown yet that this is equal, okay? To be shown later, okay? So that we just claim that the position of U2 onto the subspace W1, because that Z1 is just an orthogonal basis for W1, so that we can just write down here equal to projection of U2 onto Z1. Okay, so it's this one. So you can see that U2 is a linear combination of Z1 and Z2. So that the W2 defined to be the span of U1, U2 is actually the span of U1 and the U2. Okay. Because U2 is a linear combination of U1 and U2, and as before, U1 is equal to U1, so that this span is contained here. But conversely, Z1 can be expressed by C1, and Z2 expressed by U2, and this one because Z1 equal to U1, so that Z2 is the linear combination of U1 and U2. Okay. So the equality has been shown as before. So we have that. And U1, U2, and orthogonal basis for production. Because the Z1 and Z2 are orthogonal. Any questions? Okay. So before we proceed, we have to show this result. So that I will show a theorem, 7.2.8. So let V1, V2, up to Vk. Okay. V orthogonal basis for a subspace W of an inner product space. Then for each in the inner product space, the projection of V onto W, the projection of V onto W is actually equal to the projection of V onto Z1 plus the projection of V onto Z2 plus etc. plus the projection of V onto Z3. So that the projection of V onto W is just the summation of the projection of V onto each vector in the orthogonal basis. Okay, so that is to be the summation so that would be a linear combination of the zi's in the orthogonal basis, and the coefficient here is just this ratio. All right, so let's give a proof of this theorem. Now, think the projection by definition is in W, right? So the projection of vector V onto the subspace W is in the subspace W. So that projection W, right, is a linear combination of alpha 1, V1 plus alpha 2, plus alpha k dk, because Z1, Z2 up to dk is a basis. Okay, so also since V minus the projection of V onto W, this vector is orthogonal to W. Okay? So it's orthogonal to Y for all Y in W. Okay? So in particular, V minus projection of W inner product with Zi will be 0. Okay? For all I from 1 to k. Okay. So in particular, the difference will orthogonal to Zi. Okay? So we have V Zi, okay, minus projection, but the projection of V onto W is alpha 1 Z1 plus alpha 2 Z2 plus etc. plus alpha k zk with zi. Alright? This is equal to 0. Okay, so from here we have that. So we implies that. So now V Ci is equal to, so the summation, so we find that this is alpha 1 linearity of the inner product for the first argument. So this is V1 Vi plus alpha 2 V2 Vi plus plus alpha k Zk Vi. Okay. But Zi's are orthogonal to each other. So even though we have k terms, only one term is left, because if if one only if that Zi and Zi, otherwise for all other Zj not equal to Zi, the inner product is 0. So this implies that okay, so we have that for all I from 1 to k. So this implies alpha I is equal to V Vi Alright, so we determine the coefficient of I. So finally, the projection of V onto W becomes to the summation I from 1 to k V Vi and Vi. And this is exactly, the formula here is exactly the projection of V onto Vi. And we have done. So we prove this theorem. Okay. So if we have a subspace W and we find an orthogonal basis, if we have an orthogonal basis, that's very important, okay? We have an orthogonal basis which consists of k vectors. Then the projection of any vector in the inner product space onto W is just the sum of the projection of this vector V onto each vector in the orthogonal basis. Okay, any questions? Okay, so if no question, then I will see. Okay, so suppose that we have a WK k minus 1 equal to span V1 UK minus 1 and UK minus 1 and V1 equals is an orthogonal basis for WK minus 1. Alright, so now we go to the case step. We let ZK to be the UK minus the projection of UK and WK minus 1. The projection of that. And from our previous theorem, this is the projection of UK onto Z1 minus the projection over S to that Z2 UK projection ZK minus 1 UK. So this is UK minus UK U1 UK UK minus 1 UK minus 1 Right, so again, since the difference, since UK minus the projection of UK onto K minus 1, this one sum to y or y in the K minus 1, so that ZK orthogonal to ZI for all I from 1 to K minus 1. Okay. So that the new ZK will orthogonal to the previous ZIs, because that ZIs Z1, Z2 up to Z sub K minus 1 is in W K minus 1. So that we have a orthogonal state, and the WK defined to be the span of U1 U2 up to UK UK minus 1 UK becomes equal to the span of U1 capital K minus 1 and the ZK. Because that ZK is a linear combination of UK and a vector in WK minus 1. But WK minus 1 is the span of U1 up to UK minus 1. So from here, ZK is in here, in the span of this set. Conversely, UK is a linear combination of Z1, ZK minus 1, and the ZK. So UK is also in this spanning set. Okay, so that we can establish that they are equal. And V1, UK minus 1, and UK is an orthogonal basis for WK. Alright, and so we go on up to M. So UM is equal to, ZM. The last member in the target orthogonal set is UM minus projection WM minus 1 and then UM. Okay. Okay, so we have so this is UM minus and the W is span of oh, I forgot to say. In orthogonal. Also, we have that. Okay, so we have that. So that is the procedure. Alright, so we achieve our goal to find a orthogonal set from a linearly independent set. And by normalize each members in this orthogonal set, we will obtain an orthonormal set. Okay, and there is a theorem in the textbook, 72.2. It says that a vector Z is the orthogonal projection of a vector V in an inner product space. V onto a subspace W of V. Right? So a vector Z is the orthogonal projection of vector V in an inner product V onto a subspace of V, if and only if and only if Z is the point W closes A x minus z. The distance is the minimum of all y in W. Okay? So the minimization property, the minimum property of a point Z is the sufficient and necessary condition that Z is just a orthogonal projection of a vector V onto a subspace W. Okay, and the proof is that this theorem is equivalent to theorem 7.1.e section 1.1. Okay. So we proved a theorem 7.1.e before, and saying that any orthogonal projection has this property. So that if Z is the orthogonal projection of V onto W, then it satisfies this minimum property. Okay? So this is the forward direction. The reverse direction is that orthogonal projection is the only vector, the only uniqueness, the only vector in W satisfying this minimization property. Okay? So the reverse direction is implied by the uniqueness of the orthogonal projection. Okay? So we have shown that before, and so I will not repeat it again. Right, so please see the proof of the theorem 7.1.e. Okay. Any questions? Okay, so if there's no questions, then so this square solution alright, so we will consider this square solution. Now consider an inconsistent linear system. AX equal to B. Okay? If before, if we encounter an inconsistent linear system, we will say there's no solution at all, so we just what? We just leave the problem there. Alright? Okay, so and don't treat it. But in many situations, you still need a solution. Alright, for such an inconsistent linear system, you still need a solution. Okay? But as you know, because it's inconsistent, you have no solution at all for this equation. Okay, so let's see that it is inconsistent even only because that the B vector is not in the column space of A. Okay, so this is the basic reason that B is not in the column space of A. But we still need a solution. Alright? But this solution we know there is no solution satisfy this equation, right? So to have a solution, we will say that the best effort solution. So what is the best effort solution? Right, so here is the definition. Least square. Least square solution for such an inconsistent linear system is a solution alright, so we call a solution, but actually a solution actually is a vector x such that it will be put into here, into the left hand side x, alright? This vector has distance from B, so this is the error, the distance from B, so that is minimized. Okay, so that we put the so-called the best effort condition, the best we can do, so that we try to find a solution x. Actually it's just a vector, such that when multiplies a with the coefficient matrix ax, the distance from this column vector to B to the right hand side is minimized. Now I will explain why it's called least squares. Okay, so I make a remark here. Ax minus b is minimized if only the square is minimized. Okay? And the square and this is n from 1 to n. So the matrix, let me give the dimension here. This is n times n. The AX as component minus as component this is minimized. Okay? Because this is a column vector, okay, so that the ith component of the column vector AX minus the ith component of the column vector B, right? And take the absolute, the square of it is absolute. So this one is actually the square. So that it's called this square because the square is minimized. Okay? So that's why we call it this square solution. All right, now we know that the column space of A is the A, Z, for all Z in Cn. Okay? So this is the column space. And the B minus, and we know that B minus the projection of B onto the column space of A. Okay? It's the minimum of all Y in the column space of A and B minus 1. This is what we know. Okay? Because we want to find, AX is just a vector in the column space, in this column space. And we want that the difference of vector in column space such that has minimum distance from B. And such a vector, as we know from the previous theorem, that it must be the projection of B onto the column space. Okay? So from here, we get to an important result. So least square solution for an inconsistent linear system. Alright, so for this square solution for an inconsistent linear system, AX equal to B is just the solution, it's just a solution it's just a solution of the following consistent linear system. Which one is the solution which is projection of B onto column space of A. So we just replace the right-hand side vector B by the projection of B onto the column space of A. And this must be a consistent linear system. Why? Because this vector is already in column space of A. So of course we can find an X, right? Because column space consists of all A, Z, Z in the Cn. So there always exists one solution. So it's consistent. Is that okay? So the magic occurs because we know this property, this minimization property. Okay? So this minimization property. Any questions? And you may have many solutions because this consistent linear system may have a lot of solutions. Okay? Any questions? So now we will turn this problem into a system which is computationally feasible. Okay? Because that maybe you will say, well, how do I should find out the projection of B onto the count space of A, right? So how do I do that? Well, we can proceed to define an equivalent problem. Alright, so we already know this one, right? So AX should be the projection of B onto the corner space. Okay, so now the B minus, because AX, so now AX should be the projection of B onto the count space of A. So this vector should be orthogonal to every y or all y in the count space of A. Okay? Now, AX is already in the column space of A. You know, as a projection of A onto a column space, this vector should be in the column space of A. But when we express it in this way, then this is already in the column space of A. So the other condition is that the difference should be orthogonal to every element in the column space of A. But this is equivalent to saying that the B minus AX is orthogonal to every column vector. Okay? Where AI A1, A2, A, okay? So AIs are I column vectors of A. So this is economic condition. Right? And so that what is that? So this means that this is column vector. So the AI, so the AI transpose B minus AX must be 0. Okay? For I, okay? This is the inner product. And I have to put a bar. So in complex case, I have to put a omission here. Okay. Because this is the inner product. Okay. So the inner product between AI and this vector is here. So it's actually mixed commission transpose. Okay. AI H is AI bar transpose. Okay. So H means AI bar transpose. So this is economic condition. And so we put so now A1H, A2H, ANH, B minus AX equal to 0, 0, 0. Okay? So now we form a metric equation. We put the n identity into one identity here. And what is that? This is A transpose, A Hermitian. This is just exactly the A Hermitian. Or you will see this is A. Equal to the zero vector. And so this is AH E minus AX. If we're only AH AX equals to AH B. Wow! So now we have a linear system, but again, okay, so this is called the normal equation of the inconsistent linear system. Equal to P. Right, so initially we have an inconsistent linear system, AX equal to B. This linear system has no solution at all. Not any. But we are trying to find this square solution. And this square solution can be obtained from solving the normal equation here. So this is the normal equation. The normal equation is formed from this one by multiplying the Hermitian of A on both sides. Okay, and so this system must be consistent because we follow everything here. So this is a consistent system. Alright? And there exists. So this is the one solution. And any of the solution in the normal equation is just this square solution. Okay, and so you know how to solve this normal equation, right? Just by Gauss-Jordan elimination. You have learned from the beginning of this semester. We are at almost the end of the semester, but we still need some techniques we learned from the beginning of the semester. The Gauss-Jordan elimination procedure. Okay? And it helps us to solve these square solutions. So you see, we start from here, okay, end up with something solvable. Right? And then the solution has the property that this is to provide a column vector which is correlates to B. So the error, this is called the error. The error is minimum. So people call this error as this squared error. Okay? Any questions? All right, so you have to notice that the crucial point is here. The crucial point here is that to have the minimization, because this one is in a column space of A. This vector is in a column. So this is equivalent to saying that we want to find a vector in the column space of A which is nearest to B. But this is exactly the projection of B onto the column space. Okay, so that is very crucial, important thing. And because of that, we know how to find the x by deriving the normal equation here. Because this is just a procedure by using the property of orthogonal projection. Okay, and give us the normal equation to solve. Any questions? Okay, so now we can state a theorem to conclude our previous discussion. Here, 10910EECS205003. This square solution of an inconsistent linear system Ax equal to P is just a solution of the corresponding normal equation. A summation Ax equal to A summation P. And this normal equation, which is always a consistent linear system. Any questions? Let me make a remark. If we are considering real solution, if we are working on the real Euclidean space, then the Hermitian H can be replaced by transpose only, okay? Because you don't need the complex conjugate, because everything is real. So that just here is the transpose. So the normal equation, just that A transpose AX equal to A transpose B. But if we are considering the complex case, you should be aware that you have to put the Hermitian transpose. Okay? It's very crucial. If without the complex conjugate, you will get trouble, a lot of trouble. Okay? Now, so AHA seems very important, right? So let's define the AHA. Okay? So now what is AHA? Okay, so let's see. A1, A2, AN. So the matrix has n columns. So you know A is n times n, but AHA is together is n times n. Okay? It's n times n. So now the matrix G is n times n matrix. So it's a square matrix. Okay, so we examine this G matrix. Okay, because it's so important, right? It's the coefficient matrix of the normal equation. Alright, so it's H Okay, and A here. Okay, now here. And by transposing, this becomes to A1H, A2H, etc. A and H. A1, A2, A. Okay, so now we have a block column, right, and a block row vector. So now this matrix becomes to A1H, A1, okay, A1H, A2, A1H, and right? So this is the first row of the G matrix. And then A2H, A1, A2H, A2, and then A2H, AN, is that ANH, A1, ANH, A2, that is that ANH, AN. Okay, so now it's an n by n matrix. And the n by n matrix, you can see that the component, the entries are, what is that? The inner product of the columns. So now you can A1, A1. This inner product, A1, A1. And here is the A2, A1, AN, A1. A1, A2, 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 AN, A2, A1, AN, A2, AN, AN. Okay. So the entries are inner product of the columns. Yeah. Alright, so very special, right? Because it's about the inner product between columns of the matrix A. Okay, inner product between columns of matrix A. E is called the grand matrix. Okay, the grand matrix for the set A1, A2, up to AN of all columns of A. The Gij is actually AI H, J, so that is AJ, AI. Okay? Right? So the coefficient matrix of the normal equation is actually the grand matrix for the columns, the n columns of them. And the concept can be generalized. So let x be v1, vn, be a subset of vectors in an inner product space. So suppose we have a set, all right, and this set may be linearly dependent or may be linearly independent, whatever, and the vectors are in any inner product space. In here, we are considering quantum vectors in a Euclidean space, right? So this is special because of from the normal equation. But the concept can be generalized for arbitrary inner product space, including the function space. Okay? Now, the grand matrix G, Gij for X is defined as Gij is defined to be the inner product of Vj and Vi. Okay, so Ij you get here and Vi there. So IE, so we can define G directly by the inner product directly okay, so we can do this. All right, so we can define the grand matrix for any subset in inner product space. And so we have a final theorem. If X is a linearly independent set in inner product space, then its grand matrix is invertible. Okay? So if the S is linearly independent, say, then the grand matrix is invertible. And actually this is only condition. So the S is a linearly independent set if and only okay, maybe it's easier. So I just say if then. Okay, and approve as an exercise. Okay. All right, maybe I just write that forward direction. Okay, and there's a converse for you to discuss. Anyway, so okay. Alright, so I finished chapter 7, and so we will have New Year, right? On Friday, so that is a holiday. We are not going to have a class. So before the final examination, that will be the week, I think, will be January 13th, okay, on Wednesday. So I will cover the first section of chapter 8, okay, track, next week, okay? So, so next Wednesday we will have the last quiz. Okay, today is the last second one, right? Then we have, okay, so I stop here, and then you will have about 5 minutes break to take a rest, and then you will hold the quiz.